Hello, everyone. Today we're going to introduce lecture 17, which is separation of variables. How to use the separation of variables method to solve the Laplace equation. Actually, for this section, we're going to go through 5 examples, which will show you exactly how to use this method to solve Laplace equation. And this section in the textbook is in very detailed explanation and derives. It shows how to derive the equations to solve the problems. So I figured out it's quite in detailed in the textbook. So I strongly suggest all of you to read the textbook. But here we will go through some of the basic ideas of the separation of variables. But for detailed things, you need to go through the textbook to read all of those examples in this 3.3 section. Okay, so first of all, in this section, we will solve Laplace equation directly using the method of separation of variables. And the separation of variables is very familiar. It's very popular in physics classes because as a physicist, we use this tool a lot to solve partial differential equations and even other problems. The method is applicable in circumstances where the potential or the charge density is specified on the boundaries of some region, and we're asked to find the potential in the interior. The basic strategy is simple. It shows here. So what we want to do is we want to look for solutions that are products of functions, and each of which depends on only one of the coordinates. The algebraic details can be formidable, so we're going to develop the method through a sequence of examples. As I said, totally, we have 5 examples in this section. They are described in details. So just go through the textbook, try to understand them. Okay, now we're going to start from the first example, but remember our task. We're going to solve the Laplace equation or find the solutions for the Laplace equation, which are products of functions, and each of them depends on only one of the coordinates. Okay, what does that mean? Let's see the first example. Example 3.3, two infinite grounded metal plates lie parallel to xz plane, one at y equals 0, the other at 1 equals a. The left end at x equals 0 is closed off with an infinite strip insulated from 2 plates and maintained at specific potential V0. Find the potential inside the slot. Here's a figure. So now you have an infinite large plate at y equal to a, and another similar plate at y equal to 0. And then when x equal to 1, when x equal to 0, which is here, you have potentials for V0. And for the 2 plates, it's a V0, V equal to 0, and a V equal to 0. Now, you're going to calculate the potential inside the slot. let's use our method of separation of variables. So first of all, the configuration is independent of z, so this is just a two-dimensional problem. In mathematical terms, we first solve Laplace equation and write the Laplace equation in this way. Because it's two-dimensional example, now you have only x and y variables. So it's partial square v partial x squared plus partial squared v over partial y squared equal to 0. And now let's find or express all the boundary conditions. Number one, v equals to 0 when y equal to 0. Number two, v equal to 0 when y equal to a. So these are the two boundary conditions on the infinite large plates. And in the example, we said it's a grounded potential. So it's grounded plate. So the potential is 0. Number three, v equal to v0 when x equals to 0. This is the that is the, let's see, the closed off potential at this dark gray region. And then number four, y equal to v equal to 0 when x is infinite. Okay. So now the first step is to look for solutions in the form of products, as we said at the beginning. Now we want to find some solutions which are products of several functions, and each of the functions is independent from other variables, but depends only on one variable. Then we can write the solution vxy into a product of two functions, xx, y. So the number on the left, it's a function of x, and then this is a function of y. So on the face of it, let's see. Okay, now you can see it's simply described, this whole function is simply described by two functions, and each of them is a function of one variable. And then if we write it into the Laplace equation, then you will get y d squared x over dx squared plus x times d squared y over dy squared equal to 0. So now this is a Laplace equation. And now next, we want to separate the variables, because now on the left, you have y, you have x. On the right, you have y, you have x. So the simplest way to separate the variables is let's use the equation over x times y. So on both sides, we use the equation to over x, y. Then what you get is 1 over x dx squared over dx, d squared x over dx squared plus this term. So now remember that you just use this function over xy, or you use this term dot product 1 over x, y. And the same thing on the right side, 1 over xy. Then you get this equation. Now, if we look at this equation, you will find you have two equations, two functions. On the left, it's a function purely depends on x, and on the right, you have function purely depend on y. Now, this could be written by another type of equation. Let's see, fx plus gy equal to 0. F is a function of x, f is a function of x, g is a function of y. If x and y are independent from each other, and the function of x plus function of y equals to 0, then what does that mean? That means f and g must both be constant. Why? Because suppose if f is not a constant, then okay, if f is not a constant, you may change fx, you may change x, and then fx might be changed. Then if we held y fixed and fiddle with x, the sum of f plus g would change. So try to understand this sentence or this paragraph. So this is the key of solving the problem, because now if you separate the equation into this term, fx plus gy equals 0, and f only depends on x, g only depends on y, and x and y, they are independent, then fx must be a constant and the gy must be a constant. If this is true, you can continue to solve the problem. So this is very important. Try to understand this paragraph, read it several times and try to understand it. Now, it follows equation 3.23, and then 1 over x dx squared over d squared x over dy equals c1. C1 is a constant, and here it equals to c2. So c2 is another constant, and c1 plus c2 equals to 0. Then c1 and c2, c1 and c2 should be two constants, and one of them is negative, the other one is positive, or they might be both 0. So in general, let's say one of them is positive, the other is negative. So in this case, in this particular example, we need C1 to be positive and C2 to be negative. Why? Because you can also try make C2 to be positive and C1 to be negative, and you will figure out there's no solution. Then you need to try another solution, which is C1 positive, C2 negative. We didn't try the wrong direction. Now let's try to go through the correct direction, which is C1 positive, C2 negative. And then you will have, let's say, d squared x over dx squared equals to k squared x. K squared x means the constant is positive, and for y it's negative k squared y. So here it's negative constant. Then the solution for this function is x equals to a e kx plus b e exponential to power negative kx. And for y equals to c times sine ky plus d cosine ky. Okay, and then remember that v is a product of x times y. So v equals to this term. This is the appropriate separable solution to a Laplace equation. It remains to impose the boundary conditions and see what they tell us about the constants. Okay, so here, this is a general solution for such problems. And then from now on, we're going to take all of the conditions. Actually, we have 4 conditions. We're going to take the 4 conditions and try to determine the constant one by one. And in the textbook, it gives you a quite detailed explanation of how to determine the constant one by one. Let's see. Okay, it's in quite detailed matter. So here, let's stop here. So I'll leave this detailed derives or detailed the equations to you. You can read the book and find out how does the solution find out the constant one by one. So now you have so many constants, A, B, K, C, and D. And the general idea is finished. So for any problems, if you want to solve the potential or solve the Laplace equation, we use the method of variable separation, and you separate the two variables if it's a two-dimensional case in x and y, and then you write it into two equations. One is depending on x, the other is only depending on y. So there are two equations, and then you use some tricks to figure out for those two equations, let's say in this case f and g, one should be positive and the other one should be negative. And then for the positive one, it could be written in this term. For the negative one, it could be written in this term. And then the solution is the product of these terms times the other term. And then this is a general solution. And then later on, you need to figure out A, B, C, D, K. And using all the boundary conditions. And some of the constant might simply be zero. It becomes pretty easy. And if you want to see the details, just go through the examples in the textbook. We're not going to go through the whole details because the general idea, the scientific idea is done once you get this equation. And then you solve this equation, and then in the textbook, beside the first equation, it gives you two more equations about this method. And after all of the three equations, it gives you another two equations for solving Laplace equation using the method of variable separation, but not in Cartesian coordinates. Instead, they're in the spherical coordinates. We're going to go through some ideas of the spherical coordinates for solving Laplace equations using the method of variable separation in next class. For this class, that's all that I want to show you. But it's not finished, remember? You need to spend time to read the book and go through the other two examples, 3.4 and 3.5. See how did they find the constants A, B, C, D using the boundary conditions. Okay, so the class is finished for today, and in next class, I will give you some more examples on spherical coordinates. So that's all. Please read the textbook. See you in next class.